Well, it would not be a description of me.
I should ask here, Phil, basically, you're on camera, in the back of your head's on camera. Would you like me to blur out your image? Okay. Any questions?
Yes.
You bring it.
Okay, so on question 53, when it let the bead have charge Q, or because we only have the solution.
All right.
So it says, so let the bead have charge Q and be located distance D from the left of the end of the rod. Can I see the setup image of this question? Fair enough.
Basically, you've got a charge here, a charge here, there's a rod, and then a bead that's a distance D away.
And then the bead from the other charge is how far?
So that is 2 meters.
Okay, so then, okay. And so you just set it up same as the okay, so the beads charge is constant.
Yep.
And then the electrostatic constant is constant. So those kind of cancel out with the two positive I hat, negative I hat.
Yep.
So then you're left with just the 8 and then the 2 and then D squared and 2 meters minus D squared, which is the distance.
Yep.
And then from there, I feel like this is just algebra, but how does the the 8 become a 4?
All right, this positively charged, that's positively charged. So if this is negatively charged, then it's being repelled in both directions. If it's positively charged, try that one again. If it's negative, it's being attracted in both directions. If it's positive, it's being repelled in both directions. Either way, doesn't really matter what the charge on the bead is. So you end up with KQ1 Q of the bead over the R1 bead squared is equal to KQ2 QB over R2B squared. And as you said, they cancel out, they cancel out.
Right.
That was 8 nanocoulombs and 2 nanocoulombs. So nanocoulombs would cancel out. I'm left with 8 over D squared is equal to 2 over 2 minus D squared. This 2 from the 2 meters.
Right.
All right, and then the next bit was the part that you had a question on.
The net force will be 0 if 4 over D squared equals 1 over 2 meters minus D squared.
Okay, so they divided both sides by 2, leaving a 1 and a 4. You could cross multiply. You'll end up with a quadratic. Use the quadratic formula. That's sort of, yeah. No problem with that. That if we know it's an equilibrium in between it, we've correctly identified that it's here and not here and not there, and it has to be here because that's this problem. Then you could also just take the square root of both sides. So you're left with 2 over D is equal to 1 over 2 minus D, and you can avoid the quadratic.
Why can't you do that?
Why can you?
Yeah.
Just take the square root of both sides? The math people insist as long as.
Well, I mean, the quadratic gives you 2 answers. Why is it that when you take the square root, you get the one that you want?
If you know the correct region, I know that whatever charge this is, in order for it to be an equilibrium, it has to be between those two. What you are getting, if you use the quadratic, you're getting a solution that's going to be in between, and then a solution over here where the force is either that or that, where the forces are equal.
Yeah, I'm just wondering why just squaring it and avoiding a quadratic gives you the one inside and not the one outside.
When I take the square root, get 2 minus d, I am making the assumption that that is a positive number. And if d is less than 2, it's a valid assumption. If d is greater than 2, it's not a valid assumption.
Oh.
And so an extra minus sign would have to be thrown into it.
Oh, I see, and then that would give a larger value.
Yeah.
Okay. Interesting.
So again, you can do the square root technique if you have the third particle in the right place.
So it's always like that? It's set up like that, you're always gonna get the
it-
smaller one if you take the square root.
Yeah.
And, okay, so the one before that, 44, can you, or do you, or, okay, would it be preferable for us to use the, like, the full drawn out speed, or like the calculated? So when it comes to finding the frequency, like the work shown has like the square root and then all of the numbers. So 44, because they set the Coulomb force of attraction equal to the centripetal force,
Right.
and you can do that. Why?
Well, it's a circular orbit.
Right.
And the prediction of the Bohr model was that at the nucleus here, you have an electron here orbiting around, we assume in a circle.
Mhm.
It's the Bohr model. The force acting on it is the electric force, so that is the centripetal force.
Oh, okay.
So Fe equals NV squared over R.
Okay, so then they do some algebra and they get to where V equals the square root of Coulomb's constant times the charge squared over mass times R.
Right.
Now, are we gonna be given the mass of the,
The electron, yeah.
and so then that solution to the, so when they found the speed, they got 6.57 times 10 to the 15th hertz.
Right.
Or no, not 2.19 times 10 to the 6 meters per second. That speed, can you put that instead of having to write out, like, will affect your answer?
Wait, sorry. What?
Because the way they have it is that they essentially took the square root.
Instead of putting that big radical on in the numerator, yeah, you could put the 2.19 times 10 to the 6th.
Okay.
Assuming that is the correct answer. Yeah,
Right.
it's odd the way they did that.
Okay. And then 67, the really long one.
67, yes, 67.
Can you just walk through that one?
Let's see, so they're each 2 grams. That is a 60-degree angle. That's 10 centimeters, that's 10 centimeters. And they give 3 significant figures, everything except the angle. When the spheres have an equal amount of charge, two strings make an angle 60 degrees, calculate the magnitude of charge on each sphere. Okay. And we assume that they are each have the same charge. Yeah, equal amount of charge. All right, so it has some charge Q. Classic 251 with a small little 252 twist. Force diagram, just go through the process. So let's just take a look at this one right here. What are the forces acting on this?
Tension, gravity, and.
All right, I'm gonna nitpick one of those. I'll go with tension and electric force.
Gravitational force.
There we go, thank you. Tension would be along the line of the string. So there's the tension. That's gonna be a 30-degree angle. So if you split that down the middle, that would be a 30-degree angle. This would be the weight and the electric force.
Are we not considering normal force anymore?
Normal force with what?
I was always just used to doing like normal force when we used to do those. 51.
Yeah, if it were pressed against something, that would use normal force, but
Oh, it's, okay.
it's not pushing against anything. So yes, normal force still does exist, just not. Okay, direction of acceleration. All right, for those who are not familiar with it, what I'm going through right now is what I refer to as the Poisson method. It's a step-by-step. At this point, you probably know the shortcuts, but force diagram, direction of acceleration. What's the direction of acceleration?
Nowhere.
Yeah, nowhere, it's in equilibrium.
Oh,
Coordinate axes. How do you want to set up your coordinate system?
convention.
Positive, up or down?
Up.
Down.
Oh.
I heard up
Oh,
first.
yeah, sorry.
Left or right?
Right.
We'll call that I hat and J hat. Just make it official. Decomposition, do we have to break any of the vectors up?
Detention.
All right, so I'm gonna have my electric force going to the right, I have my weight going down to the left. It's gonna be the tension times the sine of 30 degrees. This would be the tension times the cosine of 30 degrees. Equations of motion.
T tension sine 30 equals KQ squared.
All right, one step at a time. Given our convention right here,
So for the X, it'd be the electric force minus the tension sine 30 equals 0.
yeah, and I'm going through step by step here, just out of habit. What I think you were saying is actually.
I just went ahead and moved it to the,
Yeah, and you were doing the substitution there. The other equation?
The tension cosine 30 minus weight equals 0.
All right. Now we do substitution. We have a formula for that and that, and I think that's it.
Right.
So then we get to what Ferris was saying, so we got K Q squared over R squared equals the tension sine of 30 degrees. And FT cosine 30 degrees equals mg. We assume it takes place on Earth.
Yes.
So we've got the mass is given. R we can calculate. What is R?
1.011.
Yeah. Because this is 60 degrees up here, and symmetry, those would have to be equal. It's an equilateral triangle. So that is 0.1 meters. K is given, so we have two equations, two unknowns, which is convenient. So from this one down there, I know that the tension is equal to the mass, 0.002 times 9.8 over cosine of 30 degrees. And then plug it into the second one and solve for Q. Is there a more specific question?
I think on the textbook, they divided the two equations. I got the tangent.
All right, so if I have tension sine 30 degrees equals KQ squared over R squared, and tension cosine 30 degrees is equal to mg, I could just divide the left-hand side and the right-hand side. Because the math people insist if I divide both sides by things that are equal, it's legitimate, as long as it's not 0. Tangents cancel out at that point, and you're left with the tangent of 30 degrees is equal to KQ squared over R squared mg. Perfectly legitimate. I typically do that in other problems. I don't know why I didn't do it here. I guess it's not my mood.
Why can't you divide them?
If the numerators are, these two are equal, and then I divided both sides by things that were equal.
That cancel out.
Oh, okay, yeah, I get you.
And then you isolate for Q.
Yep.
R squared in G 30 degrees.
And no doubt you'll get an answer that just makes you feel better about being a human being. That's all physics problems do.
Okay, so for 38, I get most of what it's doing, but just a quick question on, because it says in the solution, it says the force is repulsive and will result in a negative x and y component. And
Is that
then,
38?
yeah, and then it says
Okay.
the force is attractive for the other one, for the other charge, and will result in a positive x and negative y component. How can you assume that? Or is that
They set up the problem with X, Y,
okay?
and they had a positive charge here, they had positive charge here, and a negative charge there. So these are, and they wanted the force on the 5. They wanted the force on this one.
Oh,
So opposite, so they're attracted, so it's being attracted to this, and it's being repelled by that.
Can you draw a straight line and then see which quadrant it ends up in to see the positive and negative, or does that work?
Draw a straight line,
From
that's,
wherever the force is coming from, like to the other, yeah.
that's, and then that one, it's like a bit off there. Now, these arrows are not necessarily drawn properly. That fact, I can safely say that, this one, bigger than that one.
The negative on the bottom is pulling to the right, so it's gonna
And
hit
down.
down and down, it's positive and negative.
So positive X, negative Y.
Yeah,
The other one is negative X, negative Y.
so you basically have to look at the quadrant on the other side.
So you would find the magnitude of the force using Coulomb's law. Then you'd have to break it in, so then, given the dimensions it gives you, you can figure out the angle. So in essence, you have two forces in polar form, and then add them, like typically convert to rectangular form, and then add, like, it can be done in polar form if you're a fan of law of sines, law of cosines. And who isn't? I feel like there's still a question hanging out there that,
Well, it's just how do you know that it's both causing the, I guess, so the top one is, they're both gonna be negative, bottom one's.
that's a positive charge there,
Yeah.
positive charge here, so I know they repel. So it's gonna be
Both the
pushing.
I and the J are gonna be negative?
Yes,
How do you know it's not just one of them making it, or one of them that's being negative instead of an angle, so?
because of the angle, because this is the position that gives you in the book is this is in the first quadrant. This is on the negative x-axis. Because it's repelling, it has to be in that direction.
So it's gonna like push it into the third quadrant, basically?
Yeah, it's trying to.
Okay, so that's.
Meanwhile, this is pulling it towards the second quadrant,
Uh-huh.
and ultimately, it's gonna be, I think the final force is probably somewhere in that direction after you average. Is that sufficient?
I think so.
And everything,
So, not about the textbook homework problems, but when it comes to the derivations that we did in class, the calculus based,
right?
with the infinite line of charge, the sheet of charge, and the ball of charge, are those, like, is that gonna be on the test? Like, would that,
Alright, so a lot of the flash stuff that I'm expecting you to know cold, it doesn't mean I'm not giving it to you. So it would be, that type of formulas would be at the top of the quiz or top of the first page of the test. So there's no context. I just give a formula for force without telling you when to use it, so you should be able to look at it and go, okay, yeah, that's,
I get what he's asking though, because it's like the problems that we were supposed to do out of the book for the quiz were like significantly easier than those problems that you went over in class with the calculus
Yes.
and the long steps and everything, so. Like, is the test gonna be designed more like these with the quizzes, or is it gonna be designed like more advanced?
cause like, I know that you pull from the master sets, or old master sets for the quizzes, or not for the quizzes, for the tests.
the master sets come from old test questions.
Okay.
To give you a sense of what the test questions are like.
Yeah, we can just look at the old test questions.
Yeah.
So, those kinds of derivations and those problems, could we be tested on them?
Yes, it's fair game.
Fair game.
Speaking of the test, when's that gonna be?
It's tomorrow, so.
Sounds great.
We don't have class tomorrow.
I guess all of you are gonna miss it. I don't know the first test is. I mean, we still have, the first test will be chapters 23, 24, 25, and 26.
We got this one.
Yeah.
So you'll have advanced studies. I don't do surprise quizzes or surprise tests. Unless there's grounds, if you want me to just surprise you.
Well, if you do quizzes and master sets like every week per chapter or whatever that looks like, towards the end of February before you get to the test.
Yeah. That, we might double up or skip the quizzes. We'll figure it out when we get there. Other questions?